we need to move on. So our next speaker is Karen Kwitter, who's professor of astronomy and chair of the astronomy department at Williams College in Massachusetts. Karen was an undergraduate at Wellesley College. She got her PhD at UCLA, and like Dave, she spent her whole career, I won't say how long it is, I know, but I won't at Williams, and I look at the paper with discovery in astronomy, external orbits.
Thank you very much. I'm very happy to be here, and I've had a wonderful time, and I can't tell you the last time that I've listened to a theologian, a historian, a psychologist, over the course of a day and a half, and enjoyed it. Let's see, am I not playing here? Okay, I had to talk to my classicist sons. Both my children are classicists, so I've spoken to the people in the classics department at Williams, one young woman who's recently had her second child, and I've told her, you owe me 2 astronomers. In any case, they were the ones who translated this for me. On coins, it says, e pluribus unum, out of many, one. And what I want to talk about today is how astronomy and the practice of astronomy, and I dare say other sciences as well, have gone in the other direction, from one many, that it's gone from the solitary activity that's exemplified by this Dao painting from the late 1600s of the astronomer in his tattered robes poring over some volume, checking it against his globe, hoping to find the discovery that's going to make him famous. So the discovery is not so risky, I guess, as getting in a boat when you don't know anything about navigation and taking people with you to unknown worlds, but still, you sit there and you want to become famous and you want to discover something that no one else has seen before. So that urge, I think, is fairly universal to try and make one's mark. And it used to be a very solitary activity that was dictated not only by desire, but also by the fact that it was very hard to communicate and hard to send letters back and forth, and there were wars, and it was very difficult to have an ongoing collaboration with somebody who wasn't in the next room with you, perhaps. So I just want to start by giving you an example of why the state sponsorship of research is not a new thing, and we could take some lessons from our Babylonian brothers from centuries ago. This is the Amizaduga tablet from the British Museum, and incised on here are 20 years worth of observations of Ishtar, which is what we know now as the planet Venus. And this is a 7th century BCE copy of something that was probably 1,000 years earlier. The original was 1,000 years earlier. And on here, the information lets us know and tells us that they understood how Venus moves, that I'm going to show you in a second, and that Venus is both the morning star and the evening star apparition in the sky. And they also had the correct interval between apparitions as morning star and evening star. There are centuries of tablets like this with observations of Halley's Comet, what we now know as Halley's Comet, of the other planets, of eclipses, and these have been called by Jonah Lendering the longest research project in the history of the world, over centuries. So if we could have a government promise to support us over centuries while we do our projects, we'd be in pretty decent shape. So here's the story of Venus's apparitions. I just thought you might be interested. We now know, the Babylonians did not, of course, the sun is in the center, Venus orbits more closely to the sun, the Earth orbits farther out, and the orbital direction is all counterclockwise as I've drawn it. When Venus is here compared to where the Earth is, it's a morning star, because if the sun is off in this direction, then as the Earth is turning into sunrise, we see Venus off here in the morning. When Venus is an evening star, it's off here to the left of the sun, as shown in this diagram, and therefore, as the sun is setting, as the Earth is turning, Venus comes into view in the evening. And the fact that the Babylonians knew this, and they knew that every 5 times the earth goes around the sun, or we now know every 5 times the earth goes around the sun, Venus goes around 8 times. And if you do the mathematics, or basically simple arithmetic, you can calculate that 584-day period that the Babylonians knew so well thousands of years ago. Now, the leadership issue in terms of the Babylonians, the priests, the Chaldeans, handed down this information from generation to generation. And as was mentioned, learning about nature and the shamanism and having some power over nature that the civilian next to you didn't have gave you power, gave you a social status, gave you cachet. And as I tell my students, when it was important to know, for example, when the Nile was going to flood so you could plant your crops, because in Egypt you don't have the kind of meteorological cues that you get, say, in New England about the seasons changing. You had to know when to plant, and they're not going to give you that knowledge for free. The banks didn't hand out calendars, so you had no other way of knowing. And so the idea of astronomical knowledge being power was certainly the case back in the Babylonians' time, and after that the Egyptians' time, and even more recently than that. But leadership models in modern astronomy are pretty much different from what they were back then. I don't claim that these models I'm going to talk about in a second are unique or complete, but they seem to me to cover reasonable facets of the kind of leadership that I see in astronomy. And the first 2 that I'll talk about are timeless. They could happen anywhere. And the third one, which is the one that Felipe alluded to, is a modern invention. You know, the administrator, basically, is a more modern invention. So my type A is synthesis. This is what one might talk about, one might say, as a stroke of genius. Aha, I get it. Morton said in her paper that to see what everyone else has seen, but to think somewhat, I'm not saying it exactly right, but to come to a conclusion no one else has arrived at before. But synthesis is a way of looking at something and seeing it in a different way when processing and thought converge and you finally see a picture. So it's a novel idea of looking at the way something is put together. So Malcolm Gladwell in Blink would say, that's it. I got it. I know why this is happening. So it's that hit of inspiration that sometimes comes. And you can't always, well, you can hardly ever, you can't predict it, but you can pave the way for it to happen. Because if you have a well-ordered mind and you've, as I'll show you in a second when I talk about Kepler, if you're saturated with the details of the problem, things will come to you and the synthesis takes root more easily. The second kind of leadership, I would say, is leadership in method. And I would say it's a tool. It can be a hardware tool, like a kind of telescope or a kind of instrument that I'm going to talk about that you saw in my paper, or it could be a software. And I would say something like a theory would be software. Relativity is software in terms of a new way of thinking about the world and having it make sense. It gives you literally unprecedented way of thinking about the universe. And third, this is the new kind of leadership by exhortation. So it's someone who can be charismatic and compelling and be a cheerleader for a particular scientific goal. And as I'll mention later on, a part of the problem, or a problem with such a leader, is to remain connected to the science and not to be like Prince Henry, where you can get the appellation navigator, but basically it'd be better to say navigator enabler. So that's the challenge of someone who aspires to be a type C kind of leader. So I'm going to give you examples of each of these kinds of leadership, and the first one I'll talk about is Kepler. So it's a little, not quite modern, but I think Kepler really personifies some of this wonderful aha, blink moment, not once but twice. And he's also uncharacteristically honest about his failures and his successes. You know, he's willing to give himself a whack upside the head just as much as he is saying how great he is. So I think he's a good person to look at when we want to think about this kind of leadership. He derived the laws of planetary motion. His book he wrote several books, but one of them came out in 1609, so we're talking about the time of Jamestown founding, and it's interesting to put these time scales together about what's going on in the New World, what's going on in Europe, and that he worked during the 30 Years' War, and there's a story about him having to go basically duck and cover and run to the person who made the paper so he could go and give it to the printer to publish his book. And in the meantime, between publishing books, he was defending his mother against a charge of witchcraft. And the judge in the trial said afterwards, essentially, I would do anything to just get this man out of my courtroom. I never want to have to listen to him again, because he was an astrologer as well, and he was showing charts and showing why his mother should not be convicted of witchcraft. He was a genius mathematician. He used data that Tycho Brahe, the Danish observer, had gotten over decades. Observations, pre-telescopic observations of the planet Mars. Mars is the planet next out from the sun. It's the first planet that's up all night. You saw Venus was always very close to the sun, so you never see Venus too far from the sun. You can't observe it all night long, only for a few hours after sunset or before sunrise. And the fact that Mars is the next planet out means that it moves the most rapidly around the sky compared to the Earth. So it gives you a good opportunity to look at planetary orbits. So Tycho Brahe had observatories he had an observatory in Denmark that was given to him by the king on the island of Ven, called Uraniborg, and he was able to make very, very precise observations of the position of Mars that we now know were just at the limit of human vision in terms of being able to determine positions accurately, just to within the resolution of the human eye, because he had no telescopic advantages. And he was rightly proud of his observations, but he also knew that Kepler was a genius mathematician and he wasn't. And he didn't like that. And so he knew Kepler was going to break the code. He knew Kepler was going to be able to discern the secret of planetary orbits. And because of that, he was very parsimonious with doling out the data to Kepler. And he just gave it to him a little at a time. And after Tycho died, the story goes he was at a banquet with the king and couldn't get up to go to the men's room because it was impolite if the king hadn't gotten up yet. And for some reason, didn't do it after the banquet, and on the way home got into a carriage accident and died of uremic poisoning. Anyway, Kepler himself says, perhaps it was with unseemly haste that I ran into the study and stole all of his observation books. Yes, I think there was litigation, in fact. Tycho's heirs were not very happy about that. Anyway, but that's where his raw data came from. He was Tycho's assistant, and then he's worked for 20 years waging a war, his words, about trying to figure out the figure of Mars's orbit. Finally concluding that the orbits are elliptical, as everybody knows now, but it was quite a battle. And as I mentioned, he was quite honest about his shortcomings and what his problems were. And I would say, I'm not the first one to say it, but I heartily agree, that Kepler was the first, I would call him the first physicist, because he breaks with his predecessors, and he talks about causes and reasons for the planet's orbits. He wasn't what Kessler would have called a blind geometer. He wasn't just doing mathematics and doing geometry to try and figure out these orbits. He was thinking about what the causes were, and he was quite wrong. He talked about magnetism, and he might have even used the word gravity, and he didn't quite get it. That would take Newton to synthesize. But he really did think in terms of the physics of the problem and not just the geometry of the problem. So here's Kepler's deal. The outside curve here is a circle, and the inside one, you and I know, is an ellipse, but Kepler doesn't know it's an ellipse. It's just the curve, the orbit of Mars. And the other thing Kepler knows is, you can see here that the disagreement reaches a maximum right here at the horizontal line here. And Kepler knows that Mars is here in its orbit when this angle between these two green lines is a maximum. It's the angle from Mars to the Sun and Mars to the center of the orbit. It's the same angle, not the same value, but it's the same angle defined by these two black lines as well. But the point is, this angle is a maximum when Mars is here And that angle turns out to be 5 degrees, 18 minutes. What does that mean? Not much, but that turns out to be what the angle is. He also knows that the ratio of the radius of this curve here to the radius of the circle is 1.00429. That is, the distance from here to the circle is 1.00429 times the distance from the center to Mars's orbit. Notice, this is less than 1%, less than half of 1%. That's how precise Tycho Brahe's measurements were, that he could see this difference of less than 0.5% in the radius of the orbit. Okay, so 1.00429, again, not a number you're going to write down to remember for the ages, but he did this mathematics over and over and over again. And finally, as he even says, by chance, so here's luck again, by chance, he looks up at his trigonometric tables and he sees that the secant, which is just the ratio of these two lines, the secant of this angle is 1.00429. Now that can't be a coincidence. So he says he woke up as if for a dream. He now has an equation that will describe the distance of Mars from the sun at every point just given by the secant of this angle. And what we know now, but what he didn't know, was that that equation is the equation of an ellipse. But unfortunately for him, Descartes and analytic geometry were decades away. Right? Somebody in high school could figure this out now. If you gave this to an analytic geometry class in high school, they'd say, oh, that's an ellipse. Kepler didn't know that. Yes, he had flattened circle and chubby-cheeked circles, and yes. And he tried all kinds of different circles, but he still doesn't realize it's an ellipse. So now, that was his penultimate battle. Now we get to the end. So he has this equation, but he doesn't understand it. And as I said, the analytic geometry is far away. Even though he's convinced, so here's two sides of his brain. He thinks the orbit must be an ellipse, but he doesn't know that that equation describes an ellipse. So he throws the equation out. This is intellectual honesty, too, because he throws the equation out and he says, okay, I'm going to start over. I'm going to just try again and see what can happen. So he constructs an orbit that he knows to be an ellipse by geometric methods that he understands, not analytic methods, but geometric methods. And it took him a year to realize that the orbit that he's made as an ellipse is the same as the orbit that his equation has described. He just figured that out. And when he figures it out, he says, what a foolish bird I have been. So he tells you that he was just been an idiot for all this time. So the orbit turns out to be an ellipse. It's published in Astronomia Nova in 1609. And notice, here it is about the orbit of Mars. Emperor Rudolph, who's been his patron, is here. Notice he, as the author, is just sort of at the bottom down here. Everybody else gets higher billing than he does. But the idea that he has finally figured this out, and the idea that his mind had to be sufficiently prepared to realize that that 1.00429 meant something. Somebody else who hadn't paid as much attention would have just gone over their head, and they wouldn't have seen that it was, in fact, an ellipse. So he did it twice. He should get credit twice for discovering his law of planetary motion. Let's fast forward several hundred years, and I want to talk about Martin Schmidt, who also displayed this type A kind of leadership in astronomy. Notice these guys were more or less working alone. Kepler certainly working alone. Schmidt had a few colleagues, but basically it was his work. He decoded the spectra of quasars. Quasars were discovered in the 1960s. Remember, radio astronomy itself, that's radio waves from space, were only discovered in the 1930s. And so radio astronomy in the 60s was still very young. And people were discovering very stellar-looking small objects that looked just like stars, quasi-stellar, but they had radio emission, loud radio emission, so they didn't seem like they were normal stars. And also, when you took spectra of these objects, that is, you just spread their light out into component wavelengths, Kirchhoff and Bunsen had shown in the mid to late 1800s that a continuous radiation spectrum would come from a hot incandescent source like a light bulb. You send its light through a prism and you get a rainbow. That changes depending upon the temperature, but the point is it's a continuum. If you take a hot gas, like the gas in a fluorescent light bulb, and pass it through the prism, you get only light at particular colors that are fingerprints that tell you what the elements are that are emitting that radiation. And if you take a cooler gas and put it in front of a hotter source and take a spectrum, like the sun, most stars are that way. The centers are hot, the outsides are cool. So at its very basic level, this is what you have. You see the rainbow produced by the hot source with dark lines now superposed on it by the cold gas. And just as these are fingerprints, they're the same thing, one in absorption and one in emission. In one case, atoms are losing energy, in another case, they're gaining energy. But the wavelengths that are involved are the same for a given atom. So it's like a fingerprint book. Okay, most stars have spectra that look like this. But one quasar called 3C273 had a spectrum that looked like this. Yeah, this is a graph of what a spectrum would look like. Yeah, there's a continuum here, but look, there are emission lines here. Stars don't have spectra like that, so these don't look like ordinary stars. And these wavelengths were mysterious, a mystery. They didn't fit anybody's fingerprint. And we thought we knew the periodic table pretty well, that we didn't have to invent a new element, right? That Occam's razor would tell us that it's probably something common, but just under a certain circumstance that's giving us bizarre wavelengths and shifts to those wavelengths. So here's Schmidt's idea. First, let me take a little digression. We'll talk about the Doppler effect very briefly. Everybody knows what the Doppler effect is. If a fire engine or an ambulance has ever gone by you, you know what the Doppler effect is. It's a change in pitch for sound. If something is moving toward you or away from you. Coming toward you, the pitch gets higher. Moving away, the pitch gets lower. For light, it's color. Toward you, the equivalent of higher pitch is toward the blue part of the spectrum. The equivalent of lower pitch is toward the red part of the spectrum. And so here's a Volvo, not that that's critical, going at 30 miles an hour away from a listener. It's pretty quiet. No, it's not playing. Well, I'll do it for you. Ooh. Okay, it goes down. The pitch goes down. So the equivalent in light is that these spectral lines, whose wavelengths we know, whose patterns we know, are all shifted by some factor to the blue or to the red. In this case, the bottom spectrum is red shifted. All of these lines are at longer wavelengths. Okay? And in fact, by measuring the shift from their known wavelengths, once you identify the pattern, you can figure out what the velocity is. Because the higher the velocity, the bigger the shift. Okay. So Schmidt noticed that in that spectrum of 3C273, the spacing of the wavelengths decreased toward the blue. That is, they got closer and closer and closer together, those emission lines. And he also remembered that hydrogen, which is the most abundant element in the universe, has a spectrum in the optical that has decreased spacing toward the blue. The alpha line represents the transition from the third to the second energy level in hydrogen. Beta is from the fourth to the second, gamma is from the fifth to the second, etc. But notice here, alpha to beta is a bigger distance than beta to gamma, is a bigger distance than gamma to delta, etc. It's a shrinking ladder. He noticed that, and he said, let me take the ratio of my mystery lines to these hydrogen lines. And what he found, the wavelengths, and what he found was each one of these lines was redshifted from the normal wavelength by a factor of 16%. So if you take the H alpha line and shift it 16% to the red, it moves there. The H beta line goes there, gamma goes there, etc. So he had identified these mystery lines as hydrogen redshifted by 16%. He solved the mystery, decoded the spectrum. Well, solved the mystery. Astronomers are still working very hard to understand exactly what quasars are and how they work. Now we think they're giant black holes at the center of very young galaxies in the universe's history. But the point is that if he didn't know the hydrogen spectrum backwards and forwards, like Kepler knew the 1.00429 number, he might not have recognized this pattern and thought to attribute it, perhaps, or to try it as the hydrogen lines redshifted. So the idea of the, aha, let me try the hydrogen lines, that was Schmidt's moment. And as you saw on the previous slide, he got on the cover of Time magazine in 1966 for having decoded the mystery of the quasar spectra. So let me move on now to type B leadership, which I call method. And in this case, the folks I want to talk about are those who are discovering exoplanets, planets around other stars. We've often believed that other stars harbor planets around them. The question is just how to find a planet around another star. Stars are brighter than planets, they're heavier than planets. Far away, we're lucky we can see the stars, never mind any planets around them. So you have to be really ingenious if you want to figure out how to get a planet, how to discover a planet around a star. And the first one was discovered in 1994 by Mayer and Kelaz, discovering a planet around 51 Pegasi. The planet has half the mass of Jupiter, but it orbits the planet in closer than Mercury is to the sun. So we haven't found any Earths yet. We're quite a ways away from finding Earths around other planets, but Earths around other stars, I should say, but planets around other stars, we've got over 200 in the last decade or so. That's a pretty big jump from 0 to 200 in a decade, and we're finding more all the time. So how do we want to find a planet? One way you could think about finding a planet is the transit method. You just stare at a star, and if there's a planet that happens to be in the same line of sight as the star, you might see a dip. Now, it won't be nearly that extreme, right? That's a big exaggeration. You have to do very careful measurement of brightness. But suppose the planet's period is a year, like the Earth's. Are you going to sit around for a year? Is your granting agency going to give you a grant to sit around and watch for a year or less? No. In fact, we've discovered one planet by the transit method, and in the future, with spaceborne telescopes, we might be able to do better, but the odds are not with you on that. A better way is to go back and use the Doppler effect if you can do it well enough. So here's a planet and a sun and around a star, and notice the star is not stationary, but it too is moving around, not nearly as much, but moving a little bit. And so that's what we look for, is the little bit of motion in the star spectrum. So here is where the star is moving away from you. Its light should be slightly redshifted. Here's where the star would be moving toward you. Its light should be slightly blue shifted. But what kind of velocities are we talking about? These are very, very small Doppler shifts. If you would think about Jupiter, say you're on Alpha Centauri, and you're looking back at the sun, and you want to see if the sun has any planets, and you want to know how precise your measurements have to be to see if you can find this effect in the sun. Jupiter would induce a velocity of 12 meters, not kilometers, 12 meters per second on the sun with a period of 12 years. A 100-meter runner can run 100 meters in about 10 seconds. The average pace is 10.2 meters per second. Yeah, it's about 10 seconds, but 10.2 meters per second. So that we're talking about extremely small velocities, and stars are millions of miles across. And we're talking about them moving meters per second. That's sort of a human scale. So it really is quite an incredible feat to be able to do that. And the key, right, this method breakthrough, was the iodine vapor cell that can measure changes in wavelength to 1 part in 10,000, which is incredibly small. And there it is, some iodine, gaseous iodine inside a cell. The breakthrough was to take this iodine vapor cell and put it on the telescope so that the light from the star passes through the cell before it gets to the detector, so that the light path taken by the starlight and the absorption from the cell, they're the same path all the way to the detector. And here's how it works. So here's the iodine absorption spectrum. It's got lots and lots of absorption lines. Its fingerprint is very busy. Right? Lots of lines with well-known wavelengths. Okay, and here's the light from the star, typical star spectrum with some absorption lines in it. And the combination spectrum is here, and the points are observations, and the line would be a model that you have to fit. And down here are the residuals, 100 times scale, the residuals of the fit. And the idea is that you take this combination and you do a fit to a model, and the only free parameters in this model are the point spread function of the telescope, which tells you how broad it makes spectral lines. It's a function of the optics of the telescope, so you can characterize it, and the velocity of the star. So you get out from the model what the star's velocity is. And here's the most amazing thing. The detection limit is down now below, I think, 3 meters per second, and I can walk that fast, right? And if I can, you can. So the idea that something so astronomical, literally astronomical, as a star can be characterized by a pace at which a human can walk is really quite remarkable. Okay, so that's type A and B. And these two methods, or these two modes of leadership, I should say, are ones where you can't really predict them. You can prepare yourself, but by some kind of definition, they are, pardon the word, spontaneous. And I'll use the word spontaneous as its own word, and I won't worry about 1,300 or 1,500 smaller words. So the third kind of leadership, that is exhortation, leadership in a team of astronomical effort, is something that is new. So I will talk about Wendy Friedman, who led the Hubble Key project. When the Hubble Space Telescope was launched, there were 3 projects that were the science drivers. And one of them was to calculate the Hubble constant, which has to do with the expansion rate of the universe. And the method that Friedman's team used was Cepheid variables, which is a kind of variable star, and by the rate at which it gets brighter and fainter, that tells you the writing at the end of the light bulb, telling you how bright it really is. And then by knowing how bright it really is, how bright it looks, you can figure out how far away it is. Okay? Just as in a darkened room of undetermined size, if someone holds up, there's a light held up, and I tell you it's a 4-watt nightlight, and someone else holds up a bulb and says, this is a 1,000-watt floodlight, you will be able to figure out which one is closer and which one is farther. You know how bright something really is, you know how bright it looks, and you can estimate the distance, and that's the way that this works. So here is one of the galaxies, one of the 100 galaxies they looked at, found more than 800 Cepheid variables. This is the galaxy M100, and here is one of the frames that they used, and the circle, the red circle, surrounds a Cepheid variable star that you can see getting brighter and fainter, brighter and fainter. But it's not all that easy to just say, oh, it's getting brighter and fainter, it must be a Cepheid, because if you look, there are other things here that get brighter and fainter. There are cosmic rays that hit the detector that aren't stars, and the telescope moves a little bit between these exposures that are weeks apart. So it's not as simple as just anything that changes is a Cepheid variable, plus there are other kinds of variable stars. But there's one, and this is the light curve of the Cepheid variable, and you can see it's got a regular period of variation. From that, we can estimate the distance to the galaxy. And by the way, there are 2 other Cepheid variables on this picture that are changing. One of them is here. There's a whole website that gives lab exercises for students, and the other one is here. And they found 800 of these that enabled them to get the distances to these galaxies out to almost 100 million light years. So here's the answer, right? You have leadership, but then you have the result of that leadership, that the Hubble constant, that is the rate at which the universe is expanding, is 50,000 miles per hour per million light years. So every million light years out you go, the universe is expanding 50,000 miles an hour faster. Okay? In astronomical terms, it's 72 kilometers per second per megaparsec, but this is what it translates out to sort of English units. And here's the diagram that tells you how that works. This is distance, this is velocity, and the slope gives you the Hubble constant. How fast the universe is expanding. This is how we know the universe is 14.3 billion years old. So this team that Wendy Friedman led was able to finally answer the question of what the Hubble constant was. There has been a tremendous discussion among astronomers ever since Hubble first derived a value of 500 in the late 1920s, but there were lots of systematic errors that have since been beaten down, and now we know the answer is 72, to paraphrase Douglas Adams. Another kind of type C leadership that actually combines with A and B, the polymath himself, Jim Gunn, is an extraordinary person. He's at Princeton University. He exemplifies type A and B and C leadership, and even more than that. In the field of astronomy, we divide ourselves roughly into observation folks, theoretical folks, and instrumental folks. You know, people who observe, people who do theory, and people who build instruments. He does all three. And he's gotten prizes, international prizes, for his work. He is really quite an extraordinary person. The Hubble Key Project was one of the first optical big astronomy projects, big science, lots of people, 75 people total on the team. But you may laugh because there are teams that are much larger than that. But if the Hubble Key Projects were toe in the water for big astronomy, then this Sloan Digital Sky Survey, which Jim Gunn conceived of and leads, is like calling a T-Rex impolite. There's so much data, so many people involved in this, that it really, I don't think anybody else in modern, any other astronomer today could have done this, could have pulled this off except Jim Gunn. So what is it? There's a 2.5-meter telescope, dedicated telescope out at Apache Point, New Mexico, near Alamogordo. 30 charge-coupled device cameras take images in 5 filters, times 6 rows, so there are 30 cameras. There's a spectrograph that can take spectra of 640 objects at once. The data rate is incredible. The data flow from raw data out to final results is, well, the Manhattan Project is probably an over-exaggeration, but it just is an incredible feat of data management. When they do images, they get 170 gigabytes a night. That would fill up 36 DVDs worth of data, and that's just the raw data that has to then get processed. And what has happened is that there are 100 million galaxies that they want to measure the brightness of and get spectra for to get a better idea of how the universe is constructed at far out distances. And so there are so many people on this team. There are 154 authors on the data release, the latest data release paper, based at 72 different institutions in countries all over the world. And Jim Gunn is the leader. There's a partial picture, or a picture of partial collaboration at Fermilab, where some of the data is handled. So, having spoken about these kinds of type C leaders, it doesn't come without a cost. Certainly every leader, everybody who breaks a mold, everybody who takes a risk, there's a cost to themselves and to their families, etc. But type C leadership, if you really want to do the science, that's hard. Wendy Friedman, in an article several years ago, wrote that she would, when there was something big happening, which was fairly often with the data coming in from HST, she had 2 small children at home. She would work from 3 in the morning till 7 in the morning. In addition to working during the day, she would work from 3 to 7 when the kids got up so she could be there and they could take them to school. To somebody who's raised kids, that I don't think I would do anything to give up my 3 a.m. to 7 a.m. sleep, but that's what she did. And she said, if you love it, it's not hard. And that's true of anybody who's obsessed with the work that they're doing and they think it's really important and they want to do it. You do what you have to do. You're not a martyr, and you say that's the way it is. But there is a cost to this leadership, and I wanted to make that part clear because it's not only paid by the investigator, but it's paid by people around that person as well. And some functions that a type C leader has to exhibit, and again, the skill set between being a good scientist and doing the science and being a good administrator or leader, there's not much overlap in the traditional skill set. You don't get taught that in graduate school. You have to shepherd your colleagues. Okay, again, think faculty meeting, right? You have to lobby funding sources. You've got to be nice to your senators and congresspeople and the people in government and agencies. You have to politic the community because you've got to get consensus from your peers. And you have to be all of these things, which again are not taught in graduate school, for scientists anyway. Maybe they should be. So the Type C leader is really a chimera of science and administration. And the challenge, as always, is to be connected to the science. Some people do that better than others. Jim Gunn is able to do that fine, but others turn out to be science enablers, which one could argue that's a reasonable thing to do, but I think it's a disappointment for the scientist in the end. Okay, let me just talk a little bit more about the modern environment for astronomy. First, I'll give you the good news. There's been a lot of progress. We've learned a lot about the universe with the launching of space observatories and with new equipment on the ground. We've learned a lot about stars and planets and galaxies and cosmology. And as I say, there are new instruments and new facilities. But the bad news is that public funding for astronomy has fallen over the last 20 years, probably even longer than that, to the point where the national observatories cannot do everything they want to do, or what they should do, what their constituents are insisting they do, on their own. And they've had to partner with private universities, trading time or trading instrument building expertise in order to keep going. So the point is that the number of nights on telescopes, and that's the commodity by which astronomers, observational astronomers operate, how many nights on how many telescopes you get, that's diminished quite a bit. And only 20% or so of all of the possible nights open to American astronomers were open to the entire community. A lot of it has been privatized, and in fact, it's looking a lot like it did over 100 years ago when the big universities had private endowments from people like James Lick or Yerkes or Lowell to build an observatory, and the general public at large was not able to make use of those observatories. So that turns out to be a problem. And one answer to that problem is join a team, right? Get onto that bandwagon, be one of many on a team. And I'm just going to talk briefly about my own work because it's an illustration of the zeitgeist, of the current climate about being on a team and getting access to observatories that you couldn't get ordinarily. Very briefly, I work on planetary nebulae, which are the end stages of stars like the Sun. They eject their outer layers, which contain processed material from the nuclear fusion inside the star. And along with supernovae, which are explosions of much more massive stars, these are the general means of recycling heavier elements into the interstellar medium. And it's the buildup of these heavier elements over the time of the universe and the galaxy's history that have allowed, for example, human life to form. The carbon, the nitrogen, the oxygen, the iron in your bodies all came from inside stars, one way or another. Planetary nebulae, I feel like an apologist. I'm always an apologist for planetaries. Nothing to do with planets. See, these two things look very similar, right? Well, there's Uranus, and there's NGC 6720, which is a planetary nebula. Herschel looked through his telescope and said, that kind of looks like Uranus. It's a planetary nebula. Okay, so there, an apology for the ages was born. And what I study is compositions of the planetary nebulae, how these objects have gotten to be so enriched. And they have emission line spectra because they're hot gas, and we need data from space, from Hubble and Spitzer, and data from the ground in order to measure these abundances of elements from their emission line spectra. We get so much data that it's hard to analyze and hard to keep track of. I work at a small undergraduate college, and my students have actually helped me in a way, in a very important way. These are 3 undergraduates, me and my colleague from the University of Oklahoma. The undergraduates wrote this program, this package called ELSA, Emission Line Spectrum Analyzer, to take the data, analyze it, and give tables, publication-ready tables of emission line strengths and calculations at the end. and we're just about to submit this to a journal. Because we have no graduate students, our undergraduate students work very closely with us. This student here is just getting back tomorrow from observing in Chile with another collaborator of mine at Cerro Observatory. And these two fellows were working with her this summer on infrared data from the Spitzer Space Telescope on planetary nebulae. So we have a nice little group going at Williams for looking at lots and lots of planetary nebulae. In our galaxy, the planetaries are everywhere. They're in the disk, they're in the halo. We'd like to find them all, but we can't because we're blocked. If we're over here and there's a planetary nebula over here, we'll never see it through all that gas and dust. So what do? Well, is it easier? We go to the Andromeda galaxy where there's a planetary nebula. It's easy because you get a better view, but it's so far away. It's 2 million light years away, so everything is very, very faint. And so what we have done is to assemble a team that has access to telescopes that are not open to the public to be able to observe a lot of these objects. So here's our ground-based arsenal. Kitt Peak in Arizona, which is part of the national system. Cerro in Chile, part of the national system. Apache Point, New Mexico, the same place where the Sloan survey is. There's a 3.6 meter telescope that I have a collaborator at one of these institutions that owns it. And La Palma in the Canary Islands, I have a collaborator who's there. And together we get images and spectra of planetary nebula candidates in the galaxy and in the Andromeda galaxy as well. So this team-based approach is very fruitful and very fulfilling, but on the other hand, it's a team, and it's not the same as doing work yourself or maybe with one other collaborator. And the dynamic has changed, as many of you will know. If you've worked with one other person and working with a room full of other people, it's very different. But this seems to be the way modern astronomy is moving, into the idea of teams and working with a lot of folks. The telescope in in New Mexico, we run remotely. As Jeff was saying at lunch, you don't have to go to the telescope anymore. My students and I sit, this is a screenshot from my Mac on my desk at work, and here all this pink stuff, this is all the stuff from desktop widgets that allow me to control this telescope in New Mexico with my students. There's a picture of the camera on the detector. There's the slit where the light goes through the spectrograph. There's the weather, so I can see what the weather's like 2,000 miles away. And by clicking on a button, probably one of these buttons right here, I can take observations and data, and it gets FTP'd right to my desktop. And even though it's wonderful and fulfilling to get this data and to learn about the universe and the sky and all that and all the reasons that people like me became astronomers, it's a little removed, you might say, to be doing this. And so let me just finish with something that's a little closer to my heart, a picture of something like this, that when Wordsworth was talking about the stars dancing in the Milky Way, I don't think that the current version of astronomy is what he had in mind. Thank you. No. Yes. Neil Tyson, yeah. Oh yeah, no, that's true. That is very true. Well, Carl Sagan was kind of ridiculed at first when he became, Johnny Carson's astronomer. But is that true? That part I didn't know. But on the other hand, in the current funding climate, somebody like Neil Tyson, everybody wants to get on his coattails. Can I do something with you on your myriad TV shows and things? Because education is now such an important part of astronomical research. Any NSF proposal that you submit, there's got to be not just a pro forma little, oh yes, I believe in education, and I'll spread what I learn, but you have to have a program, and you have to have a a whole process for how you are going to disseminate the information you have, not just to your colleagues in astronomy, but also to the public. And that's why, coming from a small college, I may have, well, I wouldn't say call it exactly an advantage, but it's one hook, the idea that we have undergraduates. We have students who aren't even necessarily going to go on in science, but they're exposed to this kind of research. You know, you go to the public schools, you give planetarium shows, things like that. So the government is taking science education very seriously. On the other hand, Tyson and Sagan had to, get their street cred by getting PhDs and doing astronomical research to start out with. But leadership and education, I suppose that could be a separate category, although one would hope that there's an educational component to everything that these folks are doing.
I was thinking again about the importance of context. It seems like, of course I know, I don't have any real evidence to just anecdotal, but something like astronomy where the costs of things are so huge in terms of equipment, it's moving, it sounds like, kind of toward more bureaucratic leadership or collaborative at least. David might be able to do still things on his own, depending on what kind of research he is. Morton, you maybe on your own, but you also run a laboratory out. So you must be different. Is that right? Is that correct what you're saying?
That I would say the majority of it is very and even for this chapter, appropriately, we can be a single author. It's very different from a single author.
All that seems to me to have different implications for the leadership.
Jeff.
I'm curious why at the very beginning when you were looking at the type A and type B, you put Einstein in type B with methods and observational instruments. I would have thought that
He could be an A.
all the people who had a new way of looking at things.
Yeah, I guess I would put him in both. A new way of looking at things, certainly he's an A, but in terms of a method for explaining things and why things are working this way, if you use relativity, you can explain Mercury's perihelion, so it's kind of the software that lets you now understand. But I see your point.
Karen, thank you very much.
Okay.